Welcome to the Deep Dive. Today we're jumping into a really core piece of physics knowledge, thermodynamics. Specifically, we're looking at it through the lens of Feynman's lectures. Now, thermodynamics, yeah, that often trips people up. I think it's because you can describe a system like, say, a gas in a container in so many ways.
Exactly. Is the internal energy a function of temperature and volume? Or temperature and pressure? It gets confusing.
And that's our mission today. We want to show you how, with just a few key mathematical ideas Feynman lays out, you can cut through that confusion. And even better, how these thermodynamic laws become universal.
That's the goal. It's not just about gases. It works for, well, almost anything, rubber bands, batteries, even light itself. But it all starts with managing those multiple variables.
We need to go beyond just knowing what happens and really understand why the math holds it all together.
Precisely. We need a language for change when multiple things are changing at once.
Okay, so let's get into it. Where do we start? What's the essential tool here?
Partial derivatives. That's the absolute foundation.
Right, because if something, let's call it f, depends on, say, x and y, we need a way to talk about how f changes when only x changes.
Exactly, or only y. Think about pressure P. It depends on both temperature T and volume V. If you change both at the same time, figuring out the pressure change is messy.
So partial derivatives let us isolate those effects.
Yeah.
Can you remind us about the notation, that sort of curly D?
Sure. When you see that symbol, like y eta, it means you're looking at the rate of change of f just with respect to x.
Okay.
But, and this is crucial, you're doing it while holding u completely fixed, treating it like a constant for that specific calculation.
Got it. So that little subscript u tells you what's being held constant. It removes the ambiguity.
Precisely. And once you have those individual rates of change, you can figure out the total change. If you make a small change in x, delta x, and a small change in y, delta y, then the total change in f, delta f, is approximately the change due to x plus the change due to y.
So it's like left partial y times the little change in x.
Exactly. Plus left partial y times the little change in y. It's a linear approximation, but for small changes, it's incredibly powerful. It's our core mathematical tool here.
Okay, math foundation laid. Now let's bring in the physics. We take this idea and apply it straight to internal energy U.
Right. Let's view U as depending on temperature T and volume V. So UTV.
And using the rule we just discussed, the total change, delta U, can be written using the partial derivative of U with respect to T, keeping V constant, and the partial derivative of U with respect to V, keeping T constant.
Yep. That's the mathematical expression for delta U based on T and V changing slightly. That's equation 45.2 in the chapter, basically.
But then there's the physics perspective, the first law of thermodynamics.
The big one, energy conservation for heat systems. It tells us how internal energy actually changes in a physical process.
Delta U equals the heat you add, delta Q minus the work the system does, which is usually pressure times the change in volume, P delta V. So delta U equals a delta Q, delta V.
So now we have two ways of looking at delta U, one purely mathematical based on T and V, and one physical based on heat and work.
And this is where it gets really interesting, isn't it? We can use these two to define something practical, something measurable.
Exactly. Specific heat at constant volume, or CV dollars.
How does that work again? You imagine adding heat.
Right, imagine adding a bit of heat, delta Q, but you clamp the volume down, you don't let it change, so delta V is 0.
Okay, so the P delta V term, the first law, disappears.
It does, and the first law just becomes delta U equals delta Q. All the heat goes directly into increasing the internal energy.
And CVL is defined as how much heat you need to add to raise the temperature by a certain amount at constant volume. So it's the delta Q over delta T.
Precisely. And since delta U equals delta Q in this specific case, ECV must also be delta U over delta T when V is constant.
Which is exactly the definition of the partial derivative. Pickle VZ.
Bingo. So Sigma-Weyer isn't just some random definition. It's fundamentally linked to how the internal energy function changes with temperature. It connects the abstract math to a real-world measurement.
Okay, that's a crucial link. Now, the chapter brings in the Carnot cycle, not for engines this time, but as a theoretical tool.
Yeah, it's a clever trick. Feynman uses the idea of a tiny reversible cycle. Imagine a little rectangle on a PV diagram, not to talk about efficiency, but to derive relationships between P, V, T, and heat.
So you go around this tiny loop, calculating the work done, which is just the area of the little rectangle.
Right, the network. And you relate that work back to the heat that must have flowed in and out during the different steps of the cycle to make it work, using the first law.
And by analyzing that cycle, especially the heat added during one of the constant temperature steps, you end up deriving a general formula for delta Q, don't you? Equation 45.5, I think.
That's the one. It relates the heat added, delta Q, to the change in volume, delta V, the change in temperature, delta T, and importantly, the partial derivative of pressure with respect to temperature at constant volume, left partial to right.
Okay, so now we have a general expression for heat added, delta Q, derived from this cycle logic.
Yes. And that expression, combined with the first law, delta U, delta QP, delta V, and our original mathematical expression for delta U in terms of its partial derivatives, well, that's everything we need.
You put those pieces together, and what falls out?
You rearrange them, do a bit of algebra, and you can solve for something that seems really hard to get at directly. How internal energy U changes when you change the volume V, while keeping the temperature T constant. That's del O left, frac partial V right.
But wait, why is that quantity so important? Didn't we say U is hard to measure directly?
But the beauty is the result you get. The equation you derive, 45.7 in the text, shows that this quantity, left partial V right, is equal to tilde V right, VPOT.
Whoa. So the change in internal energy with volume is expressed entirely in terms of things we can measure. Temperature, pressure, and how pressure changes with temperature.
Exactly. That's the power of it. You don't need to know the nitty-gritty details of the molecules inside. Just by measuring key V and T, you can figure out this fundamental property of the internal energy. It connects the microscopic world to macroscopic measurements.
That feels like the heart of the chapter.
Yeah.
And it immediately shows why these laws are so general, right?
Yeah.
The application examples.
Take the rubber band. Stretching a rubber band isn't about pressure and volume changing. It's about force, F, and length, L.
So the work done isn't P delta V, it's force times change in length, F delta L.
Yeah.
But wait, it's work done on a system, so it should add to U.
Good point. When you stretch it, you do positive work on it. So the first law equivalent is delta U, delta Q, plus F delta L deller. The sign flips for the work term compared to gas expansion. But the key is you just swap the variables. Pressure P gets replaced by force F, volume V gets replaced by length L, and the exact same fundamental thermodynamic relationship derived from the Carnot cycle logic still holds.
The mathematical structure is identical.
Identical.
And the battery example, same idea.
Same idea. For a battery, the work involves moving charge, delta Z, against an electrical potential, the voltage, E. So the work term is E delta Z.
And this time, work is done by the battery pushing charge out, maybe, so it's minus E delta Z.
Usually, yes, if the battery is discharging. So delta U, delta QE, delta Z. Voltage E replaces pressure P, and charge move delta Z replaces volume change delta V.
It's incredible how adaptable it is. The same core principles apply across mechanics, electromagnetism.
That's the universality. Now, speaking of adapting things, chemists often like a slightly different variable, right? Enthalpy.
Yeah, H defined as U plus PV. Why invent another energy-like thing? Isn't U enough?
It's purely for convenience, really. Think about chemists working in a lab. What's often constant?
The pressure.
Yeah.
Atmospheric pressure.
Exactly. They work in open beakers often, so pressure is fixed. If pressure is constant, it turns out that the change in enthalpy, delta H, is often equal to the heat added, delta Q.
Oh, okay. So it simplifies things if you're specifically working at constant pressure, making T and P your natural independent variables instead of T and V.
Precisely. It just makes the math tidier for their most common experimental setup. It's a practical tool, not a fundamentally new law.
Got it. Okay, let's loop back to the simplest system, the ideal gas. What does kinetic theory tell us about its internal energy, Jan?
For an ideal gas, the molecules are assumed to have no interaction forces between them. They just bounce around. So their energy is purely kinetic energy.
And kinetic energy just depends on temperature, how fast they're moving.
Right. It doesn't depend on how far apart they are, which is related to the volume. So for an ideal gas, U depends only on T.
Which means that partial derivative we found earlier, the change in U with respect to V at constant T, that must be zero for an ideal gas. If U only depends on T, it can't change when V changes, but T doesn't.
Exactly. And that's a huge simplification. Remember that fundamental equation we derived. Dual left PP Euclide VP T. If the left side is zero for an ideal gas, then the right side must also be zero. So TBP Osroy lever white, VP Zolar.
Okay, so that means PPT left V plus 12 T lar.
Yeah.
What does that tell us?
That's a differential equation relating P and T at constant V. If you solve it, you find that P must be proportional to T at constant V, or rearranging P times V must be proportional to T.
PV proportional to T, that's the ideal gas law.
It is. Derived purely from general thermodynamic principles, plus the one simplifying assumption that U only depends on T for an ideal gas. It shows how the general framework contains the specific laws.
That's really neat. Okay, another big application, phase transitions. Boiling, condensation. How does thermodynamics handle that?
We again use the Carnot cycle logic, but this time apply it to the phase change process itself. Imagine you're boiling water at temperature T.
Okay, so you add heat, the latent heat of vaporization.
Right. And as it boils, the volume changes dramatically from the liquid volume V dollars to the gas volume V dollars.
So you have heat added L and a volume change, VDAL, occurring at a constant temperature T and corresponding saturation pressure P.
Exactly. By applying the Carnot cycle reasoning around this transition point, relating the work done during a tiny cycle involving a slight temperature and pressure change to the latent heat L.
You end up with another famous equation.
You do. The Clausius-Clapeyron equation. It relates the latent heat L, the temperature T, the volume change VDAL dLA, and how the saturation pressure P changes with temperature along the boiling curve. Left, right, decided.
Wow. So it directly connects the energy needed to boil something, L, to how its boiling point changes with pressure. That seems incredibly useful.
It is. It governs the equilibrium between phases. It tells you how boiling points shift under different pressures based on measurable quantities like L and the volume change.
Amazing. Okay, one last example, and this one feels really different. Radiation. Light in a box.
Yeah, blackbody radiation. The energy carried by photons bouncing around inside a container of volume V.
How can thermodynamics possibly apply here? There aren't molecules in the same way.
Well, thermodynamics applies to any system with energy, temperature, pressure, volume. For radiation, electromagnetic theory gives us a key piece of information about its internal energy. It tells us that for radiation, the internal energy is related to the pressure it exerts by 1 dollar equals 3 PeV.
Okay, $1 is 3 PeV. So we take that specific relationship
And plug it back into our fundamental thermodynamic equation, the one relating left partial V right tap to dead P and T EQ 45.7.
Right, the one derived from the Carnot cycle logic.
Yes, when you substitute Wu 3 PeV into that general equation and do the math,
What happened?
you find something remarkable. You deduce that the energy density, U divided by V, must be proportional to the absolute temperature raised to the fourth power, 4 abrupto T4 weak.
That's the Stefan-Boltzmann law for blackbody radiation.
It is, derived just from general thermodynamics plus that one input with 3 PeV from radiation theory. It shows the incredible reach of these thermodynamic principles.
So wrapping this up, we started with the need for partial derivatives to handle multiple variables.
Which let us clearly define things like CC valor using the first law.
Then we saw how the abstract Carnot cycle structure allowed us to derive this incredibly powerful relationship connecting internal energy changes to measurable P, V, and T.
A relationship that proved universal, applying equally to rubber bands and batteries just by swapping variables.
And it contains specific laws like the ideal gas law.
And gave us the Clausius-Clapeyron equation for phase changes.
And it even led to the Stefan-Boltzmann law for radiation. It's really a unifying framework.
Absolutely. The core message is that understanding these fundamental energy conservation laws and the mathematical structure that relates state variables can be incredibly powerful, sometimes more powerful than knowing all the microscopic details, because these thermodynamic laws apply so broadly.
Which leaves us with a final thought for you, listening. Feynman showed how this framework links mechanics, heat, chemistry, electromagnetism, even light. Where else might these general principles of energy, work, and state variables apply? What other complex systems, maybe even outside of physics, could benefit from this kind of structured, universal thinking? Something to ponder. Thank you for joining us for this deep dive into the mathematical machinery behind the thermodynamics. We hope it makes those equations feel a bit less intimidating and more like the powerful tools they are.